Raskar. The talk is given by Roarke.
All right, great, thanks. So, my name is Horstmeyer, and my talk is titled The Validity of the Wigner Distribution Function for Array-Based Imaging. And what that means basically is we're going to try and model diffraction effects, like effects that limited the performance of these really large lenses, simply, and hopefully I'll help you understand how. And I did this work, or Tom Cuypers wrote this paper, and so did Philippe, Bekaert, and Ramesh, Raskar, are the others co-authors. So the first half of this talk is going to be an introduction to the idea of Phasespace. And I think most of you, or I hope most of you, went to the tutorial that was given yesterday by Marcus Testor, which is on a similar subject, but I'm going to try and approach it from a different angle. And then the second half will be a couple applications of this concept, and then a discussion of its validity and how we can extend it. So I'm going to start with an example of a mass and spring, which is a simple harmonic oscillator, hopefully to motivate Phasespace. So what I'd like to do is describe the evolution of this mass bouncing up and down in 1D. But I don't really know which is a more useful description, to plot its position as it changes over time or its velocity. So what I'm going to do is go ahead and try solving for and plotting both. So what I can do, if I solve that simple equation, I would get a position that changes with the cosine of time, and a velocity, obviously, as its derivative is going to be related to a sine function. But if I plot that 1D movement in a 2D space now, what I'll see as an evolution over time is a rotation in a circle. So immediately, this kind of gives a very interesting picture and insight into how the system is evolving. I can tell that it's not losing or gaining energy because it's staying on the same trajectory as it rotates. If it was losing energy, it would spiral inwards. If it was being driven, it would spiral outwards. So immediately, I can see some very nice things about the mass and spring. So that, in general, is called a phase-space representation, or sometimes a state-space representation. And for that example, I showed position and velocity. But in general, phase-space is plotting a primary variable versus a conjugate variable, the Fourier transform of a variable. So in quantum mechanics, people do this a lot, plotting the position versus momentum of a particle, for example. But also in signal processing, you can plot the time of a wave versus its frequency to examine its bandwidth, for example. So you could also do this in optics. So you could plot the position versus momentum of, let's say, a photon and see how it changes. But for us interested in computational imaging, it's sometimes more useful to us to just plot the propagation direction of a ray, or a related variable is called the spatial frequency of a wave, which I'll explain in a second. And so just sticking for the ray example for a second, the ray-based phase space is just like a light field, which many of you are familiar with. So what I can do is simply plot the direction of a ray with respect to the z-axis against its position. So in this real space over here, it's a 1D space. I'm going to put different rays, and I can fill in my 2D space on the left, which is my light field with different points. So a good example of the light field evolving is looking at a graded index medium, or what's called a Grin medium, which could be just a concentration or sugar dissolving water at different concentrations. And here you can see, shining a laser through it, it will bend. So to understand that, you can just model the refractive index change of this Grin medium as an elliptical refractive index. And if I shoot a ray in here, I'll see again it bends down, but then it'll sort of bend back upwards if the highest index is in the middle and continue to oscillate. So plotting this in phase space, I'm going to plot the ray's change with respect to the z-axis, not time now. But you can see it's just going to rotate, just like my previous simple harmonic oscillator. So plotting these rays, and now I can shoot a bunch of rays in, and my whole light field will rotate to a focus and then rotate again. So looking at this rotation can offer some really useful insights instead of just looking at these rays sort of collapsing and expanding again. So it's a helpful tool. So what I want to do is extend this from a light field to something that works with waves so I can understand diffraction better. So to do that, you have to introduce the term of spatial frequency, or the idea of spatial frequency. So spatial frequency is simply related to a plane wave. So what I can do is plot a plane wave, And a plane wave can be also described by a bisecting angle, which is just like a ray, or a bisecting ray at a certain angle. So here I'm showing a plane wave propagating some direction right along the ray, and the ray is tilted at an angle theta. All spatial frequency is the sine of that angle divided by wavelength. So it's very similar to a ray. They're almost interchangeable. So if I went ahead and plotted this spatial frequency, or I'm sorry, this plane wave in my wave-based ray space now, I would get a line because the wave is sort of existing everywhere, but it's heading off. It has one spatial frequency. It's heading off in one direction. So if I rotated this wave, I would just expect my line to shift downwards. So the question is, how do I represent a more complex wavefront in this phase space, in this 2D light field space? So the answer you would sort of guess is from Fourier optics. If you're familiar with it, you know you can decompose a complex wavefront into a sum of many plane waves. So you'd expect something like a Fourier transform to happen. So this concept, the transform is actually called the Wigner distribution function, or the analytical transform to this problem. And so for a 1D input, f, you get this equation, and you can see it sort of looks like a Fourier transform, but there's these two variables, and that sort of helps you step it up from a 1D function to a 2D function, which is sort of putting all the math aside. You can just think of it as a joint description of a wave's position and direction, just like a light field, but for waves. So it has some really useful properties. Just like a light field, if you integrate along the angular variable, p, you get the intensity of whatever you're looking at. So here, just graphically illustrating that. And as it transforms, as it propagates or hits different things, all the transforms, or most of them, will be geometrical. So as it propagates, it just shears along the x-axis. Hits a lens, it'll shear along the p-axis, just like a light field would. And a Fourier transform is a 90-degree rotation, for example. So what does it look like? Well, here I'm just going to show a simple example of a plane wave, or a bunch of rays at theta equals 0, hitting an open aperture. So what it looks like is something like this. And so you can see it looks kind of like a light field. Most of the energy is concentrated around the angle 0 axis, so most of the rays are going to keep going straight forward. But I have this fringing going on, and the fringing is going to represent my diffraction effects. So one really useful property of this is that it's a real function. So just like a light field, it's just like a weighted set of rays. But also, it's positive and negative. So on the bottom, you can see it extends from negative 0.2 to 1. So what you can think of is this ray-based, wave-based representation as a light field, just with negative rays. So what we call that is an augmented light field. And we've been exploring this idea for a couple of years. But the general gist is you can just treat this as a light field if you just allow some rays to have negative weights. And for all intents and purposes, I'm going to just use the terms augmented light field and Wigner distribution interchangeably. I'll talk about how you can do a little extra stuff with the Wigner distribution at the end of the talk that an augmented light field couldn't do. But a simple example to illustrate this is the double slit experiment. So here is a famous experiment showing the wave effects of light. A coherent wave hits two slits, and it diffracts out, and they interfere to produce on a screen a interference pattern. So a sort of varying bright and dark spots on the right. So you can model this with rays really easily. If you just shot rays from each slit, and if they're the same length, then you'd expect a bright spot. You'd expect constructive interference. But if they were different in length by, let's say, half of a wavelength, you'd expect a dark spot. So you could do this simply by keeping track of how long each ray is, but you'd have to do it very precisely, less than half of a wavelength, to really model everything correctly. And things get complicated, you doing it with that method. So instead, what I can do is take the Wigner distribution of these two slits. And that looks something below. So it looks something like a light field of the two slits would. The two red lines would be light sort of spreading out at a lot of angles from each slit. But I have this cross term in the middle, which just comes from doing the transform. So you could just imagine that being is a virtual point source that exists in between both slits. And this virtual point source is emitting both negative and positive rays. But again, the quantity I'm interested in is intensity. So if I projected along the p equals 0 axis, I would just see what I would see with a regular light field, because all the positive and negative values in that cross term would cancel each other out. So I would just see what's at the two slits. But if I sheared this, so I'm propagating light, which, as I mentioned, is a shear of this space, and I project it again, I would get the expected fringing pattern, because that cross term is going to, the negative values are going to kind of work themselves in there. So equivalently, I could just propagate the rays from this virtual point source I invented that contains both positive and negative values. And those rays would add up at my screen to create the expected interference pattern as well. So in general, you could just simulate diffraction by creating these negative rays in these virtual point sources. And the way you know where to put the negative rays and where to put the virtual point source is given by this Wigner distribution that I just showed. And then you can just ray trace. So I'm going to show a couple applications of this concept. A forward problem of rendering and the inverse problem of trying to design some elements. So the forward problem of rendering is implementing just that concept I described, these virtual point sources that can contain negative values. And you can model effects like diffraction off of a CD, or on the right is a simple example of a little hologram on a credit card that changes its appearance as you change perspective. So the inverse problem comes from a simple camera model. So here I'm just showing a very simple camera model in 1 dimensions where I have an open aperture and I'm focusing light. It's in focus at Z0 and then it goes out of focus. So I can model this whole camera with one Wigner distribution. And that's the Wigner distribution of this open aperture. And so just like before I showed the open aperture, we have the same Wigner distribution. And then if I want to look at the Wigner distribution at other planes, I just need to do these transforms. So I can rotate it to the focal plane and then shear it. And so if I want to see the point spread function, this is a diffractive effect, at each plane, I just need to integrate along the angular axis. And I can see I'll get the airy disk in focus, and then the expected sort of blurring and ringing as I go out of focus. So what we did is sort of approach this problem from the opposite way. We wanted a desired set of point spread functions. So we wanted 1 point in focus, let's say. This is just a toy example. And then 2 points out of focus. And then 3 points out of further misfocused plane. So a way to do that is we developed this iterative optimization method, which just finds the best Wigner distribution to fully describe our camera. And that then tells us an aperture mask or a pattern to put in the lens to make that point spread function happen. So an example of that in practice is here we did the same thing except for 1 point turning to 4 points, turning to 9 points. You can see at the top. And then the mask that we get from the optimization is shown on the left. And in simulation and experiment, we get, in fact, 1 point turning to 4 and then 9. So this could be something like a very simple depth detection method, although it was just sort of a toy example. Yeah, the point is that this would only be possible. This is only possible with thinking about diffractive effects. You couldn't just model this by tracing rays normally. So briefly, I'll try and touch on the validity and extensions of this concept. So the validity of a couple extensions or valid points of the augmented light field are that it's only valid for one color at a time, but to represent multiple colors, you just need to add them up. So I can create a different Wigner distribution for different wavelengths of light, and that's going to scale my angular axis because spatial frequency, remember, depends on wavelength. And then I just add them up. So taking care of color is pretty straightforward. It's applicable in almost all propagation regions, which I'll touch on next. And we can model partially coherent light. We can extend to 2D elements, so that requires a 4D phase space. Before, a lot of my examples were just 1D situations where it's a 2D light field. And then there's a lot of other extensions using this Wigner distribution into nonlinear materials, thick elements, scattering media, the non-paraxial region, polarization. So those interested, this will be on my website. I just put a couple references up. I'm going to focus on the middle three quickly. So the validity of the Wigner distribution is in almost all regions. So the Wigner distribution is based on what's called the Fresnel approximation, which is used pretty much universally to model diffractive effects and is valid up to in most regions. And it's certainly valid in the far field, which is the Fraunhofer region. The one area you have to be careful with is called the non-paraxial region. And that's at a region that's at really large angles with respect to the element that you're interested in modeling. And the Wigner distribution is actually valid in that region as well. You just need to modify it simply. And I won't explain how, but there's a couple references on how you need to modify it. You can also model partial coherence. So coherent illumination is just like illumination from one point source. So if I put my double slit experiment to the right of this one point source, I would get the nice full contrast fringes I showed before, and my Wigner distribution would be the one I've been discussing all along. To do partially coherent light, all that means is you just have a couple point sources to the left of your double slit experiment. And these couple point sources are each mutually incoherent, but they're going to propagate and go through the slits and then create also an interference, or interference pattern, but it's going to have less contrast on the screen because the effects of constructive and destructive interference are sort of going to wash out between each point source. So to model this, all I need to do is add up 3 Wigner distributions, but each one's going to be slightly shifted along the angular variable, and that's because the waves are hitting the slits at slightly different angles. So here I'm just sort of graphically illustrating adding up 3 shifted coherent Wigner distributions to get a final one, but the term in the middle of the cross term is going to be less. It's not appearing as less, but it actually is going to be washed out because the positive and negative values will sort of cancel out. So in the incoherent limit, if I had many point sources, I would expect to see no contrast from my 2-slit experiment. It would just all be bright. And that's just like adding up a lot of these shifted Wigner distributions, so the cross term completely washes out. And then I'm left with my regular geometric light field that we're all used to. So finally, you can extend this to 4D. So the last point is a 2D input requires a 4D function to represent it in this light field space or Wigner distribution space. So a good example of that is the rotating beam. So this is an example where I can't really tease out one variable from the other. I sort of have to analyze it in the full 2D/4D light field sense. So how do you visualize this? Well, one way to visualize it is to borrow techniques from just looking at a light field, a regular geometric light field, which is you sort of tile together local angular content and view it as a 2D image. So I did that for the rotating beam, and you get something like this. So it's sort of pretty, but it's also interesting if you zoom in and look at, let's say, a local 3x3 region in the middle. You can see I get these local blobs of rays, angular content that's rotating around the center. So immediately, without having to propagate or do anything complicated, just by looking at the augmented light field or Wigner distribution of this rotating beam, I can see it has this rotating aspect to it. So I know it has what some people call angular momentum inherent to it. So it's a nice visualization tool. So in conclusion, the Wigner distribution function, sort of mapped as what we call an augmented light field where you just have negative rays, is a really useful way to model wave effects. And it's also an insightful visualization tool. It helps you see the wave effects without having to do a lot of messy integrals. And we have a number of applications from our group that we've started exploring, but it's still kind of new. So there's a lot of information at the website below. And yeah, thanks for your time.
Any questions?
Yeah, go ahead.
I was wondering if there was an advantage because of computational complexity in designing the factors and creating Wigner distributions rather than
Yeah, that's a really good question. So the question's about computational complexity. And yeah, so it's more complex in the sense that you have to take a 1D function and represent it in 2D, or a 2D function and represent it in 4D, right? But I didn't really get into it. The fact that all the transforms are geometrical, or you can simply take projections or slices of it, really help reduce computational complexity. So there's a lot of different trade-offs. But yeah, I would say in some cases it's a lot more useful. In some cases, computationally it's not. But definitely for visualization, at least for me, for looking at the problem, it's much, much more useful than trying to just propagate waves using something else.
I'm just curious, did you try out? You said it was just a testing thing. But you tried that
The mask?
utilization application for actually
Yeah.
estimation?
Yeah. So the example at the bottom is an experimental thing. I printed off the mask and put it in a lens. And it works.
It works.
Yeah.
To follow up that on the iterative aperture mask, on the iterative aperture mask where you went from 1 dot to 4 dot to 9 dot.
Yeah.
2 questions. What is the dimensions of the pattern that you
Yeah,
created,
let's see if I
and
can.
was that coherent or incoherent?
So I actually had the parameters up there. So this element is it's a 50 millimeter Nikon lens, focal length 50 millimeter. It's a 1 centimeter long aperture mask, printed at 50 micron resolution, and I just placed it directly into aperture stop. So I took the lens apart, put it in there, so it's right on the aperture plane, and it yields this point spread function. I don't know what was the other question.
Is it coherent light or incoherent?
So it's a point spread function, right? So I'm taking a point spread function measurement. So I'm imaging 1 point far away. So it's naturally going to be spatially coherent.